Hi, I'm Jigar Patel, and today I will present the AM modulation. So this is function for the RC filter. On this line, with the read function, we are reading the learning wave, and the sampling carrier frequency is 8 kilohertz, and we are sampling 4 sample per cycle. So let's run this part. So here we are modulating the signal by multiplying carrier with 1 plus k and k into m. So m is the message, and we are adding 0.05 noise. So we are generating the random number and multiplying with 0.05 and generating the M modulation. So here, so this is a waveform for the actual message. So here we are printing the showing the message on this graph. So in the next step, we'll show the carrier wave and the AM modulated signal. So let me run this step. So this is carrier wave and the AM modulated signal. So if you see the modulation, so the message is whatever the peak you see on the message, the same peak you can observe on the AM modulated signal. So for example, this two peak align, this peak is also aligned, so that indicate we are able to modulate the message correctly in AM. Here I'm showing the spectrum of message and as well as the AM modulated signal. So if I run this, so here, as you see here, this is a frequency spectrum for the message, and this is a frequency spectrum of the AM. So frequency spectrum is coming somewhere between around 10 kilohertz on both sides, and it's a peak at 10 kilohertz. So, and if you see the AM modulated signal, so signal of the carrier is amplitude of the carrier is going up and down as the time pass, so it's doing the amplitude modulation. So now I am doing the demodulation with the value of the tau as 5 into 10 raised to minus 5. So this I tuned it before to make it optimal. So this is default signal message and demodulated signal coming like the message. If I reduce the tau value, so if I significantly reduce the tau value, then it's affect the demodulated signal. So let me change this tau value to such a low number, let's say a lower number, and then run the signal. So if you see, because lower tau value, it takes significant time to discharge, and that's we are not able to getting the correct signal on the output. And if I increase the number significantly, if I decrease the number significantly, 5 into 10 raised to minus 8, there is some limiting happening here on the bottom side. So with the optimal value of 5 multiplied by 10 raised to minus 5, signals come correctly. You can see the actual wave, and let's run the, and then this I am passing the signal through the Butterworth filter, and with the filter feed, and this is a demodulated message, and I'm storing the demodulated message into AM test wave. So now we can see here, this is the original signal. This is not the correct signal, this is test wave, but actually we are storing the signal into AM test wave. So let me open the AM test wave. So we are getting correctly demodulated signal into AM test wave, and the same AM test wave we are storing here. Now let's see the effect of noise on the signal. So initially I set up noise as a 0.05. Let me this increase this noise significantly, let's say 0.9, and run everything again, and let's see how the output wave looks like. So I'm running all the steps together, and if you see, this AM test is just updated, and so basically you cannot recognize actual signal because of the too much noise. So let's reduce the noise to 0 and just make sure the quality improve significantly if we change the noise to 0. Rerun again. Okay, and so there's much less noise on the output demodulated signal. So let's switch back to the FM. So I use the same RC filter and reading the learning wave, doing this carrier frequency as 8 kilohertz. This is carrier cos 2 pi FCT, and doing the modulation. So modulation is equal to, so FM signal is equal to cos 2 pi FC time plus integral of the message. So this is as per it's integration of the message from the previous time sample, and this is the message, the same message as we saw in the AM wave. So looks like we are able to correctly print the message. And this is a modulated signal. So modulated signal, the FM, it's a 3 second wave, and the frequency, it's because of the we are not zooming it so that you can see everything as a yellow, but actually the frequency is changing. You can see that based on the frequency spectrum. So let me run the code from okay, so this portion is running. So one thing I noticed in the AM modulation, in the FM modulation, as we are using the integral, it takes a little bit time to run the to do the modulation of the AM signal. So here you can see the frequency spectrum. So frequency spectrum is varied from 0 to 20 kilohertz, and most of the frequencies amplitude is between 0 to around 7 or 8 kilohertz. So you see the higher amplitude here, and then almost flat amplitude above about 8 or 9 kilohertz. So that's and if you see this frequency spectrum of the modulated FM, so that spectrum is all over the place from 0 to 20 kilohertz. So, and it's peaking around 8 kilohertz, and this looks like our carrier. So frequency amplitude peak at the carrier, and the higher amplitude from 0 to 20 kilohertz. And this is some demodulation as suggested into the class, and this is demodulated message and storing into the FM test wave. So let's see the FM test wave. And
my CPU is a neural net processor, a learning computer.
Okay, so this is demodulated signal, and let's change some parameter and see what will be the effect. So let's first change the noise. So noise is 0.05. If we change significant noise to 1 and run all the steps and see what's the effect. It will take some time to run the integration, so we are stuck into this step. Let's wait. Okay, so now the FM, with the more noise, you cannot see the peak in the modulated signal at 8 kilohertz because of the higher noise, and most likely will not able to see hear the output. So with more noise, entire signal is we are not able to decode modulated signal. So let's change noise back to smaller value. This is a little bit higher than before it was 0.05. I changed to 0.1. let's see. So everything is running now. Okay, so now with the lower noise you can see the peak on the carrier peak on the FM modulated signal. So it's 8 kilohertz. You can see the peak and run this FM test wave.
My CPU is a neural net processor, a learning computer.
Okay, so this is a demo. Thank you.